Good afternoon. My name is Adi Aryeh. I'm from Tel Aviv University in Israel. So I'm very happy to be here. I would like to thank Benoit, Patricia, and Bob, who left already, for inviting me. Also thank the audience. I understand you are already after 100 hours, more or less, of lectures. So I appreciate that you are still here. So I'm going to talk about two topics in the next 2 hours. The first one is adiabatic frequency conversion. This will be the first half, and the second one is a different topic, also related to quadratic nonlinear optics, but it's on nonlinear holography. So let's start with adiabatic frequency conversion. And I put here this very nice picture by Escher. And this is, in fact, an adiabatic process. So what we have here, this is a fish. I've said it because, as I said, you are after 100 hours of lecture, so I'm not sure if you recognize. Anyway, this is a fish. And then, the system changes very slowly. And obviously, here we have a bird. So you cannot say when this change happened. You cannot say when this transition happened. But clearly, here we had only a fish, and here we have only a bird. So this is a very nice example of a adiabatic process. I'm going to show you how to do the same with nonlinear optics. So in nonlinear optics, we don't have fish and birds. We have light. So we can start with light, which is at one frequency, at omega 1. And we are going to change the conditions very, very slowly. And at the output, we will have not a bird. We will have a different frequency, omega 2 or omega 3. Okay? And one nice thing, you can already see it from the picture, but I will also show it in nonlinear optics. We can have full conversion. You see, there are no fish here, right? So also this will happen in nonlinear optics. I'm going to show you how to have 100% conversion. And this was also shown in experiments. Generally, this concept of adiabatic processes is very established also in other fields of physics. And the idea is the following, that we have a system, and we are in some eigenstate of it. Here, the eigenstate is fish. And then we change very slowly, very slowly. Adiabatic change means this very slow change. And if we do it, then we can stay all the time in an eigenstate of the system. The eigenstate will change because the system changes, but we are always in the eigenstate of the system. So after some time, we will be with a completely different system, and the eigenstates will be different, but we will be in this eigenstate of the new system. This is what happened here, right? So this is the eigenstate of the new system, and we just stayed all the time in an eigenstate of the system. Okay. So I need to say thank you for some people. In fact, this concept, there are two former students who were very, I think they did a very, very good job in developing this concept. Chaim Sochowski, who's now just joined back Tel Aviv University as a young faculty member, and Gil Porat. And also we had some collaborators from Weizmann Institute, Yaron Zilberberg, Dan Oron, and Barry Brunner, and also two former students in my group, Ayelet and Anat. So this is the plan for the first hour. Okay, you know everything that is needed for the first part, which is quadratic nonlinear interactions and phase matching. I'm not going to spend time on it. But then I want to show you that, in fact, some frequency process or a different frequency process, when you have undepleted pump, is essentially identical to many other two-level systems that we are familiar with. Especially, I will talk about coherently excited two-level atomic system. And this analogy is very powerful because there are many tools that were developed in order to analyze these systems. And we can now just go ahead and implement them in nonlinear optics. So for example, we can use Bloch spheric representations. We can use eigenvalue diagrams. And we can also adopt concepts that were developed in these systems. for example, adiabatic following. Adiabatic following means that we transfer everything from one eigenstate to another eigenstate. And we can do it in nonlinear optics and get very robust and very efficient conversion. We can convert, this is a very broadband process. It's now already shown experimentally to be efficient over 1 octave. So we can, for example, convert ultrafast pulses. And we can also extend it to cascaded processes. And again, we can borrow some concepts from atomic physics, like adiabatic elimination and Steerup. And finally, I will show you that this can also be done. All these parts are done. Although it's a 3-level system, I assume that one wavelength is undepleted. But we can now also extend it so that all the waves are undepleted. OK, so let's just start with something you are familiar with. So we do some frequency generation process in a nonlinear crystal, in a quadratic nonlinear crystal. And we have a signal, omega 1, and a pump, omega 2. And we assume that the pump is very powerful and the signal is very weak. So we are in the undepleted pump approximation. This means that we can convert light from omega 1 to omega 3. Omega 3 is the sum of omega 1 and omega 2. But omega 2, we can assume it's undepleted. OK? So of course, we have to maintain energy conservation. This is automatically maintained. But we also have to maintain momentum conservation, which means that the k vector, k1 plus k2, should be equal to k3. This is more difficult, as you, I think, already heard, because there is dispersion in the material. So usually when we send light, we hear induced dipoles that radiate at the new frequency. But these wavelengths that generate these dipoles have different phase velocity than the harmonically generated light. So this is the phase matching problem. And if we don't do anything, then we have some phase mismatch, delta k, which is the difference between k3 minus k1 minus k2. And therefore, the amplitude of the generated wave or the intensity, they oscillate very, very rapidly, and we don't have good conversion. So you already heard also how to solve this problem. We can do quasiphase matching, for example. We can do modulation of the nonlinear coefficient exactly at this period. And then once we do it, we get constructive buildup of the generated wave. So by now, you should be familiar with this concept. And now I can ask, is this the best option that we can get? Is delta k equals 0? Perfect phase matching? Is it really the perfect case? So I will now claim that it's not. And in fact, I will show you something which is better than having delta k equals 0. So what's wrong with this? So first of all, OK, if we are here, this is the efficiency as a function of delta k. OK, so if we are exactly at delta k equals 0, then everything is fine. We can have good efficiency. But let's say something is, we have some change in the wavelength. It could be because our source is broadband, or we can have some change in the crystal, let's say temperature change or an angle. Then we are already moving out of this optimum point. And this is usually a very narrow line. So this is a problem. But there's another problem. Even if we are here, even if we are exactly at this point, and we start to do this process, what happens is that, OK, so we start, this is omega 1, and this is omega 3. So we have some conversion from omega 1 to omega 3 as we go along the crystal. And at some point, we may get even 100% conversion. Everything was converted from omega 1 to omega 3. But unfortunately, that's not the end of the story, because if we continue, then we have back conversion. Light goes back from omega 3 to omega 1. So if we really want to have good conversion, we have to cut the crystal exactly here. And even if we cut it exactly here, let's say the next day the laser is a little bit more powerful or less powerful, so we are already not in this point. So this is not a very robust process. It's very sensitive to the power of the pump, to the length of the crystal, to many parameters. And we want to avoid this. OK, so now let's look again at this some frequency generation process. And this is the coupled wave equations between the two interacting waves. As I said, omega 2 is undepleted. So it appears here. It determines the coupling between A1 and A3, but we assume that it's, A2 is here. It determines the coupling between A1 and A3, but we assume it's constant. So this is the coupled wave equations that describe the interaction between A1 and A3. You can find them in the book of one of the organizers of this workshop. But we can write it in a little bit different manner. We just normalize the amplitude. And then what happens is that this gets a symmetric form. So I claim that this is an equation for a coupled two-level system. And in fact, there are many, many coupled two-level systems. All of them are described by the same two equations. So let me just show you some things that you are familiar with. For example, if you have two coupled pendulums, this is a two-level system. We can have, in an optical fiber, we have modes at the two polarizations, even if it's a single mode fiber, and they can couple between one another. We can have, for example, two-level system, which is coupled by light. The light is the coupling mechanism. And this is what I showed, but there are many other examples. For example, also in nuclear magnetic resonance is also a two-level system. OK, so if this is a two-level system, then there's a lot of work that was done for many years, and many tools were developed in order to analyze this system. I will especially use this two-level system because it's a very nice system. And what we can do is we can look what these smart people like Bloch, Feynman, and so on, what did they do many years ago, and then let's just use it for nonlinear optics. So let's just establish the analogy. So this is the coupled wave equation. And now it's written in a matrix form for some frequency generation process. And this is the coupled wave equation for a two-level system. So CA and CB are the population in the two levels, A and B. And then delta is the tuning of the light that couples between them. There is the light that couples between the ground state and excited state doesn't have to be exactly, its energy does not have to be exactly the difference between these two levels. So it can be a little bit more or less than that. This is the detuning. So we have a detuning here, and omega 0 is called the Rabi frequency. So in fact, there is a one-to-one correspondence between what we have here, this is a two-level system, and what we have here in nonlinear optics. So let me just do this very sophisticated animation. And we can see that, so for example, the tuning is delta K here, OK? But in fact, we can go over all the parameters. For example, the time axis, OK, this is easy because this is d to dt, and this is d to dz. So the time axis becomes the propagation axis in nonlinear optics. Then the ground state and excited state populations are the intensities at omega 1 and omega 3. The tuning, this I already showed, that the tuning is delta K. And the Rabi frequency is the coupling between the systems. So in fact, we have a one-to-one correspondence. With every parameter that we have in a two-level system, we can find the analogy in nonlinear optics. Now, in two-level systems, there are some very nice methods that were established in order to visualize the process. One of them was actually mentioned yesterday by Professor Lux, is the Bloch sphere representation. So the idea is that any state of the system, we can map it onto a sphere. It's called the Bloch sphere, but if it's polarization, it will be called Poincaré sphere. Essentially, so these are the three coordinates that define the state. I think the interesting one for us is the one that, let's say, the W coordinate. So if we are at the north pole, it means that all the energy is at omega 3. And if we are at the south pole, all the energy is at omega 1. Okay? And then the dynamics of the system is given by this equation. So G is a torque vector. So it's defined by the coupling and the delta K. And then this defines the evolution of the system. So let's say delta K equals 0. So it means that this parameter is 0. So the torque vector is just pointing at some direction along the equator. And then the state vector will just do this rotation from the north pole to the south pole. Let me see if I can operate it. So this is what I showed before, but now on the Bloch sphere. So this is perfect phase matching. So we have a.
This seems to be a bit tilted.
Well, it's not supposed to be tilted, but maybe it's the graphics is not well enough. It's basically just passing between the south pole and the north pole, and in fact, as a function of the crystal length. I don't know what this means, but let's try. So as a function of the interaction length, simply the energy goes from omega 1 to omega 3 and back again. Okay, so this is what I showed you before. Okay, so let's get back to this. Okay. Okay. So this is what this is what happens in the case of now. It actually this is a better picture. So here it really passes through the poles. Now, if there is some phase mismatch, delta K is not 0. So then the torque vector would be pointing somewhere here, and then we will have rotation, but it will not go all the way up. So this means that we will not have full conversion. This is shown here, right? So this is So we don't have full conversion. We don't go all the way from omega 1 to omega 3. We go, let's say, to there is some conversion, but then it goes back. And it also oscillates faster. Okay? Okay, so can we do something better than that? So as I said, we can take some ideas from atomic physics. And then there is this very nice idea of adiabatic following. So what is adiabatic following? We have a two-level system. And now I'll start with atomic physics, and then I move to nonlinear optics. So we have a two-level system, and now I send some light, which is detuned. Let's say the energy is less than the difference. And then we very slowly we change the energy of this pulse. And by the end of the process, we are detuned very far to the other side. So this is a adiabatic process because we do it very, very slowly. We change very, very slowly the energy of the pulse. And if we do it, we can move everything from the ground state to the excited state. Okay? So we can do the same also in nonlinear optics. So as I said, the tuning is phase mismatch. So we'll start with a very negative phase mismatch. We will change it very, very slowly. And then by the end, at the exit of the crystal, we'll have very large positive phase mismatch. And now how to change the phase mismatch? We can change the period. If it's a QPM, we can just change the period. And then we will be in this condition of adiabatic process. And there is also a condition which is, you can ask, how fast can we change? So there is a condition. Basically, it says that the rate of change should be smaller than this. This is the phase mismatch, and this is the coupling to the power of 3 divided by 2 divided by kappa. This is more or less, if you just throw this part, this is more or less kappa squared, the coupling coefficient squared. Okay, so what does it mean? It means that we can convert everything from omega 1 to omega 3, right? Let me show you now. Let's try to show this movie now. Okay, so what happens now? Delta K changes. This means that at the beginning it's pointing downwards, and then the precession is around this. But as I said, we are changing delta K. So this torque vector is slowly going up, and the precession around it is as is described here. And by the end of the process, we are at the North Pole, right? Okay. And that's it. This is, so what we did, we converted everything from omega 1 to omega 3. You remember, here everything is omega 1. Okay, I will use my understanding of French. We'll do it again. So here everything was omega 1. Here everything is omega 3. So by just changing very slowly delta K, we change very slowly this torque vector, and the state vector just processes around this torque vector. So when we finish the process, we basically converted all the light from omega 1 to omega 3. Okay, this is adiabatic following, now implemented in nonlinear optics. Okay. Okay, so this is just the same movie I showed you, but just the snapshot of what happens at the end. And so you can see now that this is the evolution along the crystal. So at the beginning, the conversion is very, 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 very weak. Then at some point, we more or less move. This is this move. We have a very good conversion from omega 1 to omega 3. But the nice thing is it stays there. It stays there. Unlike what we have before, that it goes back and forth, here it stays. So this is a robust process. Okay? And as I promised, so I repeated what Escher did, but now in nonlinear optics.
If you do too slow, it would not work, right?
So there is no, if I do it too fast, it will not work.
Yeah, you do it very slow, because then for a long time, it will be on resonance with the torque vector in the...
Yeah, so I have to, okay, I have to maintain, sorry. I don't know, where is it now? Where is it? It's gone. Sorry, okay, here it is. I have to maintain this condition. Okay, this is the condition. This is the adiabatic condition. I have to start with very negative delta K, finish with very positive delta K, and the rate is given by this. If I do it, everything is okay. Okay, so as I said, I can do what Escher is doing, but in nonlinear optics. I start this, instead of birds, I have only omega 1, instead of fish. And instead of birds, I have everything in omega 3. And also you can say that this is, when we started, omega 1, we had very large phase mismatch. So the two, omega 1 and omega 3 were not coupled. So omega 1 was an eigenstate of the system. And we changed very slowly the conditions. And here they are again, omega 1 and omega 3 are decoupled. So here omega 3 is again an eigenstate of the system. So it also maintained this argument that I'm staying, if I change slowly enough and stay with, I will stay with an eigenstate, I can end up with a completely different condition. Okay, so this is just to show some differences. So this is the periodically poled crystal, and this is a adiabatic crystal. So for example, the wavelength acceptance. So here we have very narrow acceptance. This is now for real numbers for a KTP around 1.55 micron. And here you can see that I can maintain 100% efficiency over a very wide bandwidth. Okay, I can do also the same with temperature, angle. I will show some experimental results later. So this is a narrow band process. Here is a broadband process. This is very sensitive to changes in pump wavelength, pump power, almost every experimental parameter. And this is a very robust process. Okay, now you can ask, what happens if I don't satisfy the adiabatic condition? So this is the adiabatic condition. So what happens if it's not fully satisfied? So in fact, there is, even then I can find some solution. This is actually there is a criteria which is called Landau-Zenner criteria. If I just, again, if I throw this part, so the ratio between this one and, as I said, this becomes k to the power of 2. So the ratio between them is k to the power of 2 divided by d delta k dz. So, so if this is much larger than 1, then everything is OK. But if it's less, then this would be the efficiency. This is the Landau-Zenner criteria. So if I fully satisfy this criteria, I get 100% of conversion. But if I'm not fully there, then the efficiency will be smaller. And this is the same thing on the Bloch vector. OK, there's another nice tool that we can use for, again, we can borrow ideas from atomic physics. And this is in atomic physics, it's called level crossing diagram. I'll call it eigenvalue diagram. And the idea is the following. So again, these are the two wavelengths. These are A1 and A3 are the two amplitudes of our process. So we can make a small change in coordinates. And then the coupled wave equation will get this form. OK? So now what I can do, I can plot the coupled wave equation. Sorry, I can find the eigenstate of this wave equation in two cases. One, when there is coupling. So when kappa is, when this kappa 1, 3 and kappa 3, 1 are non-zero. And the other case, when there is no coupling. Actually, when there is no coupling, it's very simple. Because what we have is just delta k 0, 0, 0. OK? So times A1, A3. So what we have is delta k times A1. And I can write it this way, 0 times A3. OK? So this means that delta k is one eigenvalue, and 0 is the other eigenvalue. OK? So now let's draw the diagram in two cases. In one case when there is coupling, in the other case when there is no coupling. So this is how it looks. What I'm doing, I'm changing the period of the polling. So when there is no coupling, one of them is 0, as I showed here, and the other one is just delta k, which changes linearly because I'm changing the period. So it's almost linearly. Then I change the period. Then so at some point this would be exactly 0. This will the QPM k vector will cancel the delta k of the crystal. But if I'm a little bit less than that or more than that, then it will be positive or negative. So this is the black lines are what we have when there's no coupling. And then the blue lines is the same when there is coupling. When K13 and K31, I take the actual values. So now how does it work? So as I said, if it's an adiabatic process, I can start with an eigenstate of the system, and I will stay all the time. I can stay all the time on an eigenstate of the system. So so now the system is there is coupling. So I start here. It means that I start with omega 1, and then I change the period. So I move along this. I move along this curve, and this is the end of the crystal. So I moved from omega 1 to omega 3, OK? And I have now full conversion. By the way, if I reverse the crystal, if I just flip it, actually I think this is the next one. So this is if I just flip it. So in one case the period is going up. In the other case the period is going down. So in this case I start here. I start with omega 1. And I end with omega 3. In the other case, I start also with omega 1, but now I start from this side, because at the beginning, the period is like 15 point something. And then I move along this line, and I I also move from omega 1 to omega 3. So in this case, it doesn't matter if I have up chirp or down chirp, it's the same. Okay? Later I will show you a case where it's not the same. So this is just a trigger for the next. And in atomic physics, these black lines are sometimes called the bare state, and the blue lines are called the dress states. Okay, so this is, but we can, even if we don't know anything about atomic physics, we can just go ahead and use this because it's very simple. So this is the evolution of the intensity. So I1 goes from, basically goes to 0, and I3 gets all the energy. Okay, there's 100% conversion. Okay, so now let's show you some experimental results. So I think this was our first experiment, was 2008, where we just took a pump, which is 1064, and a signal, which was around 1.5 micron, and we used the chirped KTP crystal, periodically poled crystal. It's not periodically poled, it's chirp poled KTP crystal. And then we do some frequency generation. So this is the result. So already it shows that we can get very good efficiency. Why we don't get to 100%? Because at this point the crystal broke. But at least it shows that it follows the right trend. It's very, very robust. I mean, we can change the wavelength. Here we change it over 175 nanometers. Nothing changes. We change the temperature over more than 100 degrees. Nothing changes. So it's very robust. Okay. Later, this experiment was repeated, but with a much more powerful laser in the Franz Kartner group in MIT. So here they really got to 100% efficiency. Okay, this is, I don't know if it's 100% or 99%, but anyway, it's very high. Okay, I don't know if it's matter, if it's exactly, it's actually very difficult to say how much is different than 100%, but it's clear that it's very high. And also you can pump with less power, and then it follows this Landau-Zellner criteria. And the other thing you can already see, this is a very broadband process. You see, you have the same efficiency from 1.5 to around 2.7 micron. 100% efficiency over 1,200 nanometers, which is not bad. But I'll show you better results later. Okay, then we can ask, so far we assume that everything is CW, but what happens if there is a short pulse? In fact, there are two length scales. One is the length scale for this process. So we go from omega 1 to omega 3. So let's say this transition occurs over a relatively short part of the crystal, and this is the effective length. Now, if we have a short pulse, there is also an effective length for this pulse, which is the GVM length, which for a width of tau is tau divided by GVM, the inverse of the group velocity difference. So how do we maintain the adiabatic condition in an ultra-fast pulse? So the criteria would be that the GVM length should be much larger than this length. Okay, this is written here. Now, if we put the typical numbers, this means that we need more than about 1 picosecond. So of course, this means that, so it doesn't mean that I cannot use a 10 femtosecond signal. What should I do? I should implement similar concept to what was presented with for OPCPA. I take the pulse, I broaden it, then I do the conversion, and then I recompress it. Okay, so I just have to broaden it to be more than about a picosecond, and then it will work. So again, this was our demonstration. So we use the Tie-Sapphire laser with 30 femtosecond. We stretch it to about a few picoseconds, and then we mix it with the pump in either in KTP or in stoichiometric lithium tantalate. And then we can do either up conversion or down conversion, okay? So, and basically we can take the entire pulse and we can convert it. So this is a down conversion to the mid-infrared. And this is up conversion to the blue, Okay? So basically, we can take the entire bandwidth and can convert it. Now, here the efficiency was about 10%, and here the efficiency was about 50%. But this is just because we didn't have enough power of the laser. So, but Franz Carter does have these problems. So he repeated these experiments with a broader pulse. And in this case, the conversion is over more than 1 octave. So you can see this. What we have here is a Ti-Cepha laser, which basically is amplified in this OPCPA and goes to the crystal. So we have some radiation in this range, 0.7 to 0.9 micron. And we have a pump, which is a 12 picosecond, 1047 nanometer laser. And then they are mixed in a chirp-poled lithium niobate crystal. And basically, you can get, this is down conversion, so you get it in the mid-infrared, but essentially you get from 2,000 to about 5,000 nanometers. So it's more than 1 octave conversion. And also, you can recompress the pulse. And then they show that it's only 4 cycles after the compression. So this shows that you can have very broad conversion, and you can work with very short pulses. OK, so now, so far we discussed only a single process. But let's go one step further, and let's talk about multi-process interactions. So there are, in fact, 4 cases. We can start with some input light at omega 1. Then we can go to some intermediate frequency, omega 2, and then to an output, omega 3. So these are two up conversion process, or we can do 2 down conversion process, or we can do up, down, or I can do up, down, or I can do down, up. Okay, I think these are all the cases. Okay, so the first question is why bother? I mean, why not just go directly from omega 1 to omega 3, right? Or from here to here. So, actually, it's not always possible. Let's say I have a 1 micron laser, and I want to go to the UV. So I have to do first second harmonic. I get to the green, and then I have to do another second harmonic. I have to get to the UV. So this is and the same argument can also go if I want to do down conversion. So I cannot always go in one step very far. But also I cannot go in one step very near. Let's say I want to move, I have some frequency here, and I want to move only 1 terahertz. So I could say, OK, let's take a 1 terahertz source, which is not very easy. Let's find a crystal, which is transparent in the near infrared and the terahertz, and mix them. Is very difficult. The other option would be to do everything in the optical range, and then I can go down and up, or up and down, and move very little. So if I want to move very little, or I want to move very far, it makes sense to do a multi-process. But also it's interesting from the physics point of view. So if we already agreed that a single process is like a 2-level system, so this would be like a 3-level system. And then there are many nice tricks. Again, I can take all the tricks that were done in atomic physics, and now I can use them in nonlinear optics. For example, I will show you. We can do any one of these processes where the intermediate frequency is dark. Okay, I can go from omega 1 to omega 3, and omega 2 is dark all the time. Why is it interesting? Let's say omega 2 is absorbing. Actually, there is one specific case which can happen, where when I start here, okay, I do up conversion, so this can go to the UV. Maybe the crystal is extremely absorbing there, and then I go back. But if it's dark, I don't care. It can be 100% absorption, nothing happens. I will show you. It does not hurt the process. OK, so the concept we are using, I will show you 2 ways how to do this conversion with a dark intermediate stage. Dark intermediate stage. Okay, so the first one is actually implementing the concept of Steerup in nonlinear optics. So you don't have to know anything about Steerup. Let me just tell you what is done here. So we have two processes. We go from 1 to 2 and from 2 to 3. So each one of these processes there is some coupling. That describe it. So what I will do is I will design a crystal so that the coupling will change, again, very slowly, adiabatically, along the crystal. So the coupling from 1 to 2 will be, at the beginning, will be very, very low, and it will increase. And the coupling from 3 to 2 will be very high and will decrease. This looks strange, actually, if you look at it the first time, because you can say, OK, we start with something at 1, at the omega 1. So why we do anything here? I mean, there's nothing here. But actually, this is the way it works. Also in atomic physics, this is the way it works. So in this case, there's no experiment, but there is simulation. So the wavelengths we chose, we go from 546, which is in the green, to the UV, 340. This is this is highly absorbing. This is simulation for KTP, so it's highly absorbing already. And then we go back to 400, which is blue. So this is 546, okay, as we propagate. So it goes from our initial power all the way to 0. Everything was moved, almost everything went to 400. And you can ask, where is the intermediate frequency? Where is the UV? So it's actually here. It's hard to see it, so we expand it by about 10,000. And you can see that there is a very, very weak signal here. But it's basically dark. So although we take here the real numbers, we take the real absorption of the crystal, it doesn't matter. We can have full conversion, despite the fact that our intermediate state is in the ultraviolet. OK, there's another way to do it. This is called adiabatic elimination. So adiabatic elimination, we use, again, we have two processes. So we start with lambda 1 plus lambda pump. We get an intermediate frequency. And then we take this intermediate frequency, and we add lambda pump. So we get lambda 2. So in this case, we use just a periodically poled crystal. And we chose the period so that both of these processes are highly phase mismatched. But the sum, delta K1 plus delta K2, is almost 0. OK, you can do it if you are selecting the right wavelength. You can have, in one place it's positive, and the other place is negative. And so this is what is called adiabatic elimination. In this case, you can go from lambda 1 to lambda 2, while the intermediate frequency is dark. And this we already showed, we also showed in experiment, not in simulation. So we start with mid-infrared, around 3 microns. Our intermediate wavelength is here at 786. And the lambda 2 is in the blue, it's 450. And so this is a simulation. It just showed that, in fact, there is nothing. There's nothing here in the intermediate frequency. And this was also shown in experiment. So we can get the blue light. We could not measure the intermediate wavelength. It was below the resolution of below the sensitivity of the detector, which was about 52 nanowatts in our case. OK. Now let's go one step further. So now we want to do cascaded processes, but also we want to have them broadband. Again, we start with omega 1. We add a pump. We go to omega 2. And then, OK. So let's start here. We go from omega 1 to omega 2, and from omega 2 back to here. This is one option. But with the same pumps, we can go from omega 1 to a different frequency, omega 2b, and then go back to omega 3b. Okay, because we just basically send a signal and two pumps. So how will the process work? Whether it will do first the up conversion or first the down conversion. This I can show you. This depends on the orientation of the crystal. So in fact, this is an interesting case in which if the crystal is up-chirped or down-chirped, we get a completely different result. So in one case, this is, let's call this down-chirped. Then this is the spectrum that we measure. So we actually have this process. And if it's up-chirped, then we get this process. So in fact, by just changing the orientation of the crystal, we can select whether it will first do some frequency and then different frequency, or vice versa. This also works in experiments. Okay? So now let's use this understanding of the level crossing diagram in order to understand why in one case it works in one way, in the other case it was in a different manner. So we start with omega 1. Okay, we start with omega 1. First, we'll go in this direction where the polling goes up. So we start at omega 1. We follow the dressed state. We go to omega 2a. And then we continue. This is omega 2a. So we get eventually to omega 3a. So we are in this process. We go from omega 1 to omega 2a and back to omega 3a. Now, what happens if we go in the other direction? So if we go the other direction, the polling period starts with a large number and goes down. So we have to start here. So we started with omega 1. We go now to omega 2b. Before, I just remind you, we went to omega 2a. Now we go to omega 2b. And now we continue. So we go from here, and we go from here, and we end with omega 3b. So in one case, we started with omega 1, and we first had some frequency with pump 1, and different frequency with pump 2. Whereas here we had first some frequency with pump 2 and different frequency with pump 1. So this just is determined by the direction of the crystal. Usually it does happen, but if we have cascaded process, then the direction of the crystal will change. Okay, so I should say now, so far we assume that there is one, there is a pump which is undepleted. But in fact, recently this theory was extended by Gil Porat. And in fact, now we don't have to use this assumption anymore. So we can have full conversion. We can have full conversion both in second harmonic generation, which was not possible before, because we cannot do 100% efficiency without pump depletion in second harmonic. But also we can do some frequency generation or different frequency generation with the depleted pump. So this is an example of second harmonic generation. So we can have, if we do it, we can have 100% efficiency in second harmonic generation. And same for some frequency and difference frequency. Okay, so this was really recently. There was a report. This was in last Clio. I didn't see the paper yet. I don't know if it's coming or not. And this was done by Jacobi is the first author, but this was in the group of Roberto Morandotti. So in this case, I don't know if you can see, there is an LBO crystal, and here the change in delta K is achieved by a temperature gradient. So in one case, they heat the crystal. In the other place, they cool it. And then there is some gradient of temperature, which gives a gradient of delta K. And in this case, they can get around 60% efficiency in second harmonic, 62. And this is a more recent result. In fact, very recent. It was last week. And then in this case, we use type 2 KTP. It's not periodically pulsed, it's a chirp pulse KTP. And the reason we do type 2 is because we can change the angle of the pump, and then we can move from the undepleted pump approximation, where one polarization can be considered the pump, and the other polarization can be considered the signal. And if we go to 45 degrees, then they are equal. So we are at the fully depleted case. So we can change, we can look at different polarization, and we can get about, again, about close to 80% And also we can show that it's very robust. We can change the temperature, and the efficiency is almost unchanged. Okay, so I want to say it's not only limited to, we don't have only to do chirped modulation. There are other concepts that enable broadband robust conversion. This was done by the group in Bulgaria of Rangelov and Vitanov, where they, again, they actually take a concept which was developed in NMR of composite pulses. So here, instead of pulses, they just do steps of different periods in different segments of the crystals. But it's not something which changes it's not some linear chirp. They have some fixed lengths, and in each length they have some different period. And this provides a robust and broadband conversion. Okay, so let's summarize this part. So I hope I convince you that there are many advantages to adiabatic frequency conversion. You can get extremely large bandwidth, more than 1 octave. You can have nearly 100% conversion efficiency. It's insensitive to pump intensity, crystal temperature, crystal angle, almost every parameter of the experiment. It's insensitive. You can also do cascading. This enables conversion to absorptive bands using concepts like Steerup and adiabatic eliminations. If you do broadband conversion, then the result depends on the crystal orientation. And this also was extended to fully nonlinear conversion. If you want to read more, there is a relatively recent review article that we wrote in LPR on this topic. Okay, so this is the end of the first part, and I will be happy to take questions at this point. So I'm going now to talk about nonlinear optical holography. And so this is a concept that, so holography is an old concept. Okay, it was invented in 1948 by Denis Gabor. He got a Nobel Prize for it. It's, you know, you're all familiar with it. And what I want to show is that it actually is possible now to extend this concept to nonlinear optics. So what does it mean? So in general, in holography, what we do is we have some, this was the original idea. We have, let's say, some film in which we record some information about a wave, both the amplitude and the phase. And then we illuminate this, so this is the hologram, and then we illuminate the hologram with a reference wave, and we can reconstruct what we recorded, okay? So we can get the full amplitude and phase of the wave that we recorded. And then this was extended to computer-generated holograms, so we don't have to use a film. We can just compute the right function, and we can print it. And what I want to show now that is actually can be done with nonlinear optics. So what does it mean? It means that my recording, this is the hologram, this is a nonlinear hologram. So I will record. The recording will be modulation of the second order nonlinearity. And if I do it correctly, then I will illuminate with a reference wave at one frequency, and I will reconstruct. I will get a general wave, any shape that I want, both amplitude and phase, but not at the original frequency, but at a new frequency. It could be a second harmonic or some frequency. And so this is a nonlinear hologram. And this can be done both in space, in the spatial domain, and in the spectral domain. Okay? So again, I have to thank many people. These are former students. Tal Ellenbogen is also now a faculty member at Tel Aviv. Ido Dolev, Asya Shapira, Irit Yuviler, Noah Volach Bloch, Ayelet Ganani Padovich, and Karen Shemer. They are former students, and these are current students. So you can see many people worked on this. I'm not going to show all the results, but I'll show some highlights. So as usual, we start with quasi-phase matching, but I will show you quasi-phase matching in a different scheme. I don't think, I think you did not see it in the configuration I will show now, okay? And which is longitudinal and transverse setting and nonlinear diffraction. I don't know if anyone, I don't know if Marty Fair talked about it. No, okay. And then we will just remember what is holography and computer-generated holography, but then I will show you how to do it with nonlinear optics in 1 dimension and in 2 dimensions. And then we will do it also in the spectral domain. And then this is the last part is super oscillation. Who knows what is super oscillation here, by the way? No one. Ah, you know. Because I told you yesterday. Okay, good. So it's good because also we are under the auspice of the Joseph Fourier. Yes, so it's related to Fourier. It's faster than Fourier. So so this you know. This is quasi-phase matching, right? I don't have to repeat it. Now let's take now the crystal, and instead of going this way, let's go in some other directions. So let's go this way, okay? What happens? Then if we send light from this direction, I can actually show you an experiment. This is what we see on the screen. We see 2 points. This is the second harmonic. This is pumped by YAG. So we see 2 points, and at different temperatures, these 2 points are at different locations. And what we have here is also quasi-phase matching, but now this is a vectorial condition. So this is the fundamental. Now the k vector, the QPM vector, is orthogonal to the input wave, and therefore we get it at an angle. And because it's symmetric, we get 2 points. Okay? So this is also called nonlinear Bragg diffraction. Why? This is a triangle, so we can define here some angle alpha, and then the projection of K2. So K2 times sine of alpha should be equal to G1, and K2 times cosine of alpha should be equal to 2K1. Okay? We have to maintain these 2 conditions. And in fact, if you calculate the angle, you will find that it's exactly identical to the Bragg diffraction angle that you have in linear diffraction. I mean, if this was just a grating with a period lambda, and you will send light, then the diffraction will be at exactly the same angle, the same conditions, but now it's in the second harmonic. And it's interesting, so Freund also did the Mobius. He also proposed the Mobius ring that I think Boyd talked about. But when he was much younger, in 1968, he already showed this result. And then this was forgotten. And then after 40 years, it was rediscovered, okay, as usual. Okay. Now we can also do another thing. We can rotate. So before we started this way, then we can rotate now. Before I showed you propagation in this direction, but we can also propagate in this direction. So what do we see on the screen? This is what we see. So we see a series of points near the axis, and then we see very far. We see 1 or 2 very bright spots as well. So what do we have here? So let's start first with these points near the axis. So what happens here? You can check it, but in fact, what we satisfy here is we satisfy only the transverse condition. This means that the projection of K2 in this direction is a K vector of the crystal. So it could be first order, second order. This is why we have several points. But we don't satisfy the other condition. We don't satisfy the projection of K2 in this direction is not 2K1. So this is not a phase match process. Okay? Although it's not phase match process, clearly you can see that there is very bright second harmonic. It's visible, I mean, with not very high power. And in fact, this condition is again, there is a linear analog. It's the Raman-Natt diffraction. So exactly the same angle that you have in Raman-Natt diffraction. Raman-Natt is what you have when you have diffraction from a very thin crystal. You get here the same condition. Okay, so this explains these points. Now what about this one? So this one is the other condition. The other condition is shown here. So the projection of K2 in this direction is 2K1. Okay, but here it's not satisfied. And what's nice about it, because it's not satisfied here, I can have different crystals. It doesn't matter, because it doesn't matter what is the Pauling structure, because it's just a material. This depends, K2 and K1 depend only on the material. They don't depend on the QPM modulation. So you can see I can have different structures. In all of them, I get the same ring. Okay, the same ring, the same angle. And this is Cherenkov radiation, nonlinear Cherenkov. By the way, what I have here in the middle, this is Raman nut that I discussed before. Now, why is it Cherenkov? So Cherenkov radiation is a radiation that happens when we send a particle that moves faster than the velocity of light in the material. So then you will get a cone of light, which is the Cherenkov angle. Here it's the same thing. The omega, what generates the nonlinear polarization, moves faster than 2 omega. So therefore, we get this, basically we get a shock wave, an optical shock wave. So this is why it's called Cherenkov radiation. By the way, there are other analogs. For example, when you have an airplane that passes the speed of sounds, then you hear this boom. This is exactly the same shock wave, but with an acoustic wave. Here it's with optical wave. OK. Now, this I think also you know. This is quasi-phase matching, how to do quasi-phase matching. So you can do it in different methods. I think ferroelectrics is electric field polling in ferroelectrics. I think Marty Fair talked about it, right? It's very well-established technique. You can, and you can have it in the best crystals. These are really the best crystals in the near infrared and in the visible, like lithium niobate, KTP, and so on. And why did I show this slide? Because, OK, you can do periodic polling. You can do chirp, as I showed previously. But in fact, what I want to say is you have out of the 3 axes of the crystals, you have full access to 2 of them. So the X and Y axis of the crystal, you can do essentially any modulation that you want. OK, the third, the Z direction, you don't have access. OK, so this is a limitation we have to keep in mind. OK, now let's just remind ourselves what is holography. So here is how to make an hologram. So I have this object. I want to record it. So what I do is I send the light. It's reflected from the object. And then I mix it with a reference wave, which is just a plane wave. So originally, this was done on a photographic plate. And then if I write this, what I have here, so I have this reference wave and the object wave. But the important part is this mixing term. So the mixing term, we have amplitude and phase modulation of some carrier wave. The carrier wave is just the mixing of, let's say, a plane wave that would come from here and a plane wave that will come from here. So this is a recording of an hologram. And then we can reconstruct by illuminating it. And then we will see it. For a viewer, it looks as if there is a real object here. And we get both amplitude and phase. OK? And of course, you don't have really to do it. You can just calculate you can just calculate this and go ahead with the printer and print it. Right? You don't have to do this. It took, by the way, the idea was at 48, but computer-generated holograms was only in the 60s. So it took some time. But I guess also computers were not so widespread, not to mention lasers and so on. So it took some time to realize that you don't have to actually do this experiment. OK, so again, I remind you, this is the important term. This is the important term. These 2 are not so important. So there are 2 main ways to do it. If I can have continuous, if I can print in some continuous manner, then I can just take this expression and print it. And this would be an hologram. In many cases, I cannot do it. I can have only binary modulation. So there is a very nice way to do it. I will explain it in a minute. Where here there are only 2 values of the transmission, only 1 and 0. And this still will work very nice. You can get very nice holograms. So how does it work? Well, you see that there is this carrier frequency, and there is the phase, and there is this offset function. which this offset function is encoding the amplitude. So let's try to understand how it works. So this is the interferogram that I have, okay? Now, if I would ignore this, then it means that I can take the sign. I want to make it a binary function. So I can say, okay, let's take the sign of this function. So whenever it's, so there is some line here. So whenever it was more than 0, I will give it a value of 1. When it's less than 0, I will give it a value of 0. But then I will maintain the phase information. I will lose the intensity information or the amplitude information. So this guy, Ray Honley, he came with a smart idea how to find the clipping function that will also maintain the amplitude information. So if we are above this red line, we will give it a value of 1. If we are below it, we'll give it a value of 0. And how to find this clipping line? Okay, so this is the idea. So basically, this is a periodic structure function, so we can write it using a Fourier series. And then, so this is the phase, and this is the amplitude. And usually, we are interested only in the first order term. So we can just use this with m equals 1, and this would define our clipping function. And this works really nice. It's really nice. You can, with binary modulation, you can get then you can get both a recording of both the amplitude and the phase. Okay, so now let's show you some, now let's move to nonlinear holography. So I'll show you how to make some beams with it. And let me spend a few minutes on this beam, which is very nice. I spend a lot of time studying it. So this is called self-accelerating Airy beams. So what's special about this beam? So it's called an Airy beam because if you look at the input plane, then this is an Airy function, okay? And if you let it propagate, it maintains its shape. It means in every plane, it's an Airy function. But you can see that it bends, okay? It bends. It follows a parabolic trajectory in free space, okay? This is, by the way, there's an exact solution of the Paraxel-Helmholtz equation. So this is why it's called self-accelerating, right? We are usually used to beams that propagate in straight lines. This is a beam that propagates in a curved trajectory. It also has some other nice features. It's if we had infinite energy, which unfortunately we don't, then it would be a non-diffracting beam. It will maintain its shape. It can recover from if you block it, it can recover, so on. So have very nice features. So this is the way this is the way the amplitude is described. So AI is the Airy function, and you can see this x minus z squared. This is the acceleration. Okay, this is this is the amplitude as it propagates in free space. So how people make Airy beams in linear optics? So the idea is that the Fourier transform of the Airy beam has a cubic phase. So what they do is they start with a Gaussian beam. They put some phase mask with a cubic phase, with an SLM, for example. And then they do Fourier transform, and they get the Airy beam. Okay? So now just to warm up, let's show how to do it with nonlinear optics. So the idea in nonlinear optics, we're going to replace this SLM with a nonlinear phase mask. Okay? So how we can control the phase? It's very easy. This is a QPM grating. You're familiar with it. So let's take another QPM grating, but shift it by a small amount delta. So this gives us a phase shift. Okay? So now we'll just not make a constant shift, but we'll make a shift which is a cubic. And this will give a cubic phase, but at the second harmonic. And then we do Fourier transform, we can get an Airy beam. Okay, so this is some experiment we did a few years ago. So this is a nonlinear crystal. And you can recognize so in every cross-section I will make here, it's a periodic structure. But if I look in this direction, it's a cubic phase. So therefore, I send light. I get here second harmonic. It's quasi-phase match, but it has a cubic transverse phase. And then I do a Fourier transform, and I can get an Airy beam, okay, at the second harmonic. This is, by the way, a top picture of the crystal after selective etching. So you can see the modulation of the nonlinear coefficient. Now, nice thing about nonlinear optics, you can not only generate beams, you can also control their properties. So for example, if with the same crystal you can do either up conversion or down conversion. In one case, the cubic phase will be with a minus sign. In the other case, it will be with a plus sign. So in one case, you will get a beam that accelerates upward. In the other case, it accelerates downwards. So it means that by not changing anything in the crystal, just changing the light, the input light, you can determine the direction of acceleration. This also works in experiment. So this is up conversion. In this case, it's second harmonic. And this is down conversion in the same crystal. OK, so we saw how to modulate the phase. Now how to modulate the amplitude in nonlinear optics. So the tool that we have is the change of the duty cycle. If we change the duty cycle, so this is the best option is 50%. Then we have highest conversion. But if we want less intensity, we want to modulate, so we'll just use some other value. Let's say if it was 75, then we reduce the amplitude by about 30%. And this is the way it depends. This is the Fourier coefficient. The way it depends on the duty cycle. So actually, we can get every value that we want between 0 and the maximum value, which is about 0.63. OK, so now we have all the ingredients to make a full hologram, both amplitude and phase. So I'll show you some examples. This will be more, as I will progress, it will be more and more difficult. So let's start with a simple 1D case. So again, this was what I wrote before. OK, this is what I wrote before. But I remind you, with nonlinear crystal, I have only two dimensions. I have only two crystal axes that I can modulate. So I have to sacrifice one of them. So this method I will show is suitable for 1D beams. Also, the airy beam I showed you was a 1D beam, by the way. But this is more general. This gives also amplitude, not only phase. So I would like to have some modulation that has this shape. So there is some carrier wave, there is phase, and there is amplitude, as I showed you before. So this is in y direction. And what I do in the x direction? The x direction, I need to do QPM. So I need to do periodic modulation. OK? This is periodic modulation. Just make sure that I have good efficiency. And this is the x direction. And in the y direction, I have this modulation. So this is an example. You can see that there is some, again, in every direction, in every cross section, you will have a periodic structure. This is what gives the QPM. But if I look in this direction, I will have this function. So you can actually recognize that there is some carrier frequency, and it's modulated with amplitude and phase. So this is just some examples. I need to select functions which are 1D. So these are Hermite-Gauss beams. So for example, again, this is an experiment and theory making Hermite-Gauss beams. OK, so this was one dimension. Now let's go to 2 dimensions. So for this, I have to rotate the crystal, because only then I will have 2 dimensions that can be accessed for modulation. And in this case, the modulation is binary, because I can have only plus chi2 or minus chi2. So I can use the method I showed you before, the method of wave only. And so instead of modulating the transmission, I modulate the second order nonlinearity. And what I'm using here, I'm using this Raman-Nath phase matching, which is not a perfect phase matching, but it's still fairly efficient. As I said, if you take a crystal, you can do this experiment. If you have periodically poled crystal, just rotate by 90 degrees, you will see. You see it in the lab. It's very easy. So these are some. So this is the way the crystal looks like. These are some beams that we generate. So for example, so now this is 2-dimensional structure. So these are Hermite-Gauss beams, and these are Laguerre-Gauss beams, OK? Generated at the second harmonic. There is one problem with this. The efficiency is not very high, OK? I will show you how to improve it a little bit. But this is because it's not a phase-matched process. Now let's talk a little bit about this Laguerre-Gauss beam. So I think you had the talk of Miles Paget, so you know much more than I do at this point. But in any case, the important thing for us is that these beams, they have azimuthal phase, which goes as exponent of IL phi, well, L is an integer, and they carry orbital angular momentum, h bar L. So what happens when we send such a beam? So first of all, we can generate these beams in a nonlinear process. In this case, the nonlinear crystal, this is the hologram, has a fork-shaped grating. I think maybe you Miles showed it for SLMs, that they often use this for generating a vortex beam. But here, this is not an SLM. This is a nonlinear crystal. So this is the modulation of Chi2. This is not a very good picture, but you can also, I'll show you later a better picture. But it shows that there is actually a fork grating. So so first of all, if you send such a beam, then you will get vortex beam. Okay, this is the 0 order, but at the first order and maybe in the second order, which is hard to see, here you get vortex beams. And also there is a very nice conservation law. So twice the orbital angular momentum of the fundamental plus the orbital angular momentum of the crystal is the orbital angular momentum of the second harmonic. So I don't know if this reminds you of a different phase matching process. The regular QPM has the same shape, but instead of the orbital angular momentum, here I have the linear momentum. So it's exactly the same, but instead of K, I have here L. And in this case, this is with L equals 0, but it also works with L, which is not 0. So we can start with a beam, we can generate some vortex beam, and then we can mix it in the nonlinear crystal. And then, so this is the phase matching, so the orbital angular momentum matching condition. And you can take different cases, and you can see that it actually works. So let's say, for example, I start with LG 20. So I have here 2. I have 2 times 2 is 4. But here I have minus m of minus 2, and the crystal is also 2. So 4 minus 4 is 0. So if I go to the minus 2, I should get a beam which doesn't have any hole. It should be a regular Gaussian beam. And it works also for other cases. Also, you can control the radial index in this manner. And you can mix. You can also do non-collinear interaction. So then, this is what is called the virtual beam diffraction. It's called virtual beam because basically you send one fundamental beam in this angle and one fundamental beam in this angle. So this beam generates this diffraction pattern. This beam generates this diffraction pattern. But there's another one here in the middle. It's called virtual beam because there's nothing here. But in fact, this is just a some frequency generation process. So you can also generate and then of course you can have different angular momentum in each one of them, and then you will get the sum here in the middle. Okay, so I said the efficiency is not very high, so how can we improve it? So the reason we cannot close the triangle is because we cannot make periods which are small enough. Okay, maybe in KTH you can, but we cannot. So we are in this condition. This is 2K1, and this is the QPM vector, and this is K2, and triangle is not closed. However, we can rotate the crystal, and then with the same G, we can get QPM. So then everything would still work. We can have one-dimensional or two-dimensional modulation, and this would be about 5 orders of magnitude more efficient than what I showed you before. It's still 10 to the minus 6 percent per watt, which is not very high. But if you have a powerful enough laser, then you can get to the few percent conversion efficiency. So these are for examples in 1D and in 2D. Okay, now this is some recent result, not yet published. So in fact, what I showed you so far was off-axis holography. The reason off-axis holography is very popular in linear optics is because you get what you want in the first diffraction order, whereas in the 0 diffraction order, you have some garbage. So when you work off axis, you can get rid of it. But if you do nonlinear optics, you can work also on axis. Why? Because the garbage is at omega, and you can just put a filter and work at 2 omega. So, okay, we designed it. We didn't really make the Taj Mahal with nonlinear optics, but we made some other things like all kinds of structures, which are not very far from the Taj Mahal. So, okay. Now, there are some alternatives. I'll just mention them. I mean, let's say you don't want to do nonlinear optics. I mean, this is trivial, but still, I think I should mention it. So there is another possibility. Let's just take a periodically poled crystal, or it can even be a birefringently poled crystal, and then take the facet, and we can functionalize it. So we can put some, let's say we can put some metal or some mask, and we can write with focused ion beam. And these are some examples of things that we can do. We can generate vortex beams, lenses, pinholes, and so on. So this is, you can say this is obvious. The nice thing is you don't lose anything. You can say you don't lose anything because you have a perfect crystal for the second harmonic, and everything is in one device. You don't have to separate with the different lenses and pinholes and so on. So these are some experimental results showing this concept. And the other alternative is, again, let's stay with the fixed crystal, but modulate the input. So we can, if we have an SLM, then we can modulate the input, the pump, and generate and then maybe we can generate the desired wave at the second harmonic. So if the crystal is short, it's actually quite easy. Why? Because when the crystal is short, what you get, you have some phase, transverse phase of the fundamental. You just get twice this phase at the second harmonic. So you decide what you want, you divide it by 2, you put it on the SLM, and it seems to work. So these are some Hermite-Gauss beams. This is not shown very well, but this is an Airy beam, so you can do it. But this works only for about a crystal which is a 1 millimeter or 2 millimeters. What happens if you need a longer crystal? So then you can still do something. You can do some iterative search. For example, here we use the genetic algorithm in order to find what is the required input beam in order to propagate in a long crystal, in a 10 millimeter crystal, and get a desired beam at the second harmonic. So again, these are some Hermite-Gauss beams. Also, lenses can be done this way. It cannot work for very sophisticated beams, but for relatively simple beam, it works quite nice. Okay, so now I want to move from spatial domain to spectral domain. So the same concept of holography works not only in space, it also works in spectrum. Why? Well, let's look at the difference frequency or some frequency generation with undepleted pump. So this can be shown very easily that in fact the amplitude as a function of delta k is simply the Fourier transform. I will show you later exactly this, but it's the Fourier transform of the nonlinear coefficient as a function of space. So what does it mean? Now we can now take this nonlinear coefficient. So if we just do periodic modulation, that's the standard QPM. But now we can consider this as a carrier, and we can add to it phase modulation and amplitude modulation. It's the same equation I showed you before, but now it's used for spectral shaping instead of spatial shaping. And then we can generate any desired spectrum. And the spectral shape of the crystal can be controlled, both in amplitude and in phase. So these are already some experimental results. So for example, this is as a function of the wavelength. Here we wanted to make an Hermite-Gauss 2 function. Here we made an Airy function as a function of wavelength. So this is the efficiency of the crystal as a function of wavelength. So in fact, you can control it. You can fully control. And also here it's shown only for the amplitude, but you can also control the phase. So could be useful, let's say, for chirp, to add chirp or remove chirp, or in general to do temporal shaping of pulses. Okay, so now because we are under the auspice of Joseph Fourier University, so it's time now to talk a little bit about Mr. Fourier. This would be my last topic. So this is a very nice concept. Michael Berry is a Sir Michael Berry, and I think he has very good talent to define, some phenomena with the right name, which is very important because I can tell you that other people have done similar work before, but they didn't have the right catchy name, and so. Anyway, so the idea is to what does it mean faster than Fourier? So let's assume that we have some function which is band limited. What does it mean it's band limited? So let's say this is a function of f. There is some maximum frequency, f0. Okay? And now I do a Fourier transform. So I can get it as a function of space or time, depending on. So I will get something here. Okay? Now, if this is the maximum frequency, f0, then there's a question: what is the fastest rate that this function can change as a function of time? So anyone knows, except those that I talked with in the pub yesterday. Anyone wants to make a guess?
1 over f0?
Yeah, this is what people usually think, that this cannot be faster than 1 over f0. Okay? Well, I ask what's the fastest. Okay, it doesn't have to repeat. Maybe here it can be something else. Okay? But can I find somewhere where it oscillates faster than 1 over f0? Yeah, well, f0 is the bandwidth. Okay, so the answer is yes. I mean, it can oscillate as fast as you want, It doesn't matter what is f0. Why? Because the Fourier transform is an integral from -infinity to infinity. So maybe somewhere here, it oscillates extremely fast. Okay? But when you do the Fourier transform, there are some other parts of the function that takes care of it. And then it will work. But still here, if you just like here, it can oscillate extremely fast. So Berry has a nice example. He says, let's take the Fifth Symphony of Beethoven. And then we can transmit it on a 1 Hertz bandwidth. So we'll have the entire symphony, okay, like 1 hour at 10 kilohertz. And then we'll have some other things. And this will be a 1 Hertz signal. I can transmit it, and it will work. Okay? So this is why it's called faster than Fourier. So now let's see if we can do something with it in nonlinear optics. So this, because the fact that it's 1 Hertz does not prevent the function in time to oscillate 10,000 times in a second. It does not prevent it. As I said, you can have oscillations which are much faster than the maximum bandwidth. I will show a real example. I will not show with the symphony. I don't know how to do it. I'll show a simpler example.
So in the integral, there are negative and positive contributions, so it goes to 0, so it doesn't show up on the...
Yeah, in the Fourier transform. I'll show a very simple example in a minute. Sorry? Well, there is some problem. You need a lot of energy to do it. Okay, but still it's a nice concept, and I think it can be also useful. Okay, so this is actually the example I wanted to show. This is something you can understand very easy. So let's take a cosine. Let's take a cosine function. Okay, this is a cosine function. So of course, this is a band-limited function. Now let's remove some offset from it. So instead of looking like this, it will look like this. Okay, so this is still a cosine, right? Nothing changed. Now let's take the square of this function. So the square of this function will look like this. Right? So of course, this here and here, we can have oscillations which are much faster. I mean, the rate of oscillation just depends on the offset. I mean, if, yes?
But you said rate of change, which,
yeah, the oscillation as a function, this is, let's say, as a, sorry? Yeah, as a function of time, it can oscillate, here, it oscillates much faster than the 1 over the bandwidth, okay? This is a very simple example. So this is what's written here. So I just I'll start with a cosine, I remove some offset, then I take the square root of it, and this oscillates much faster than the 1 over the maximum frequency. Okay, now this is what I said before, that the Fourier transform, there is this Fourier transform relation between the nonlinearity as a function of space and the efficiency as a function of delta k. So if we just have a fixed, just have a homogeneous crystal with a fixed nonlinearity, then the efficiency is just a sink of delta KL divided by 2. If it's QPM, it's the same, only this sink is shifted to a new spatial frequency, right? Okay, so what now? Let's do super oscillation. So the limit here is in space. We have something which is limited in space. But if we apply the right modulation, we can have it in delta k to oscillate much faster than 1 over L, 1 over the length of the crystal. This would be the implementation of this idea. And I already have the function, right? I just need to take this function and use it. So this would be a special case of a nonlinear hologram. Okay, so this is this cosine, shifted cosine. So in fact, the Fourier transform of this cosine looks like this, but I cannot use delta function for nonlinear modulation. So I just do a convolution with some rect function, and this is already the modulation. This is the modulation of the crystal, and this crystal will be a super oscillating crystal. In fact, you can understand this is now the nonlinearity as a function of space. So there are 3 regions, 1, 2, 3. In the middle region, we need to have a pi phase shift with respect to the 2 other regions. So you can already see it. You see that there is this difference. This is the middle range, the middle section, and these are the 2 outer sections. So there is a pi phase shift between them. And also there is a different amplitude. There's a different amplitude here and here. And this is manifested by the different clipping. So there is a factor of 2 here that you don't have. Okay? So it's, in fact, with what I told you so far, you can fully understand why this is the function. And now this is just experiment, so it works. So this is the blue line is the sink of delta KL over 2. It doesn't look like a sink because I show it in a log scale. And the green line is this super oscillating function. So this is a simulation, and this is experiment as a function of wavelength, also as a function of temperature. So you can see that this is oscillating much faster than 1 over L. Okay, so in fact, the length of the crystal is not a limit to how fast or how narrow can be the bandwidth of the acceptance. And how can you use it? For example, you can let's say you have some narrow-spaced signals, and you want only one of them. So you can get rid of those that you don't want, by putting them here at the zero efficiency nodes. You will just get rid of them, and you will remain only with the signal that you want, which will be here. Okay? Okay, so I think it's a good time for me to stop. So just to summarize, I showed you that we can, using modulation of nonlinear coefficient, we can not only do harmonic generation, which you know, but we can also add functionality. Functionality could be spatial shaping, spectral shaping. We can also control the parameters of the beam. I showed you control of the acceleration in airy beams and control of the angular momentum in vortex beams. And if we do it in the spectral domain, so we can also control the acceptance, the spectral acceptance and thermal acceptance of nonlinear crystals. So maybe I'll stop here, and I will be happy to get some questions.